SN2 is a very important mechanism in organic chemistry, and you will find many reactions saying that this follows SN2 mechanism. I have written the meaning of SN2 here. S means substitution, N is nucleophilic, and this is a bimolecular reaction. So SN2 substitution is very easy to understand. What is this nucleophilic that we will see first? So a nucleophilic reaction is a reaction which involves this nucleophile, and a nucleophile we generally represent by this symbol Nu and say a negative charge on it, or it sometimes has a lone pair also. So it's basically a negative ion or a species which has negative charge or a lone pair over it. And the meaning of nucleophile will be its positive loving, or nucleus which has a positive charge, nucleus loving species. We'll take some examples of nucleophiles first. We can call OH negative as a nucleophile because it has that oxygen can have those lone pairs here, and the negative charge because of that. Another example is the cyanide or isocyanide ions, which are ambident nucleophiles because they can have negative charge here as well as on nitrogen. Then you can have CH3O negative, which is the methoxy ion. So from alcohol, if you remove this hydrogen, then you are going to get this RO negative. So alkoxy in general, you can call it. These are all nucleophiles. And a nucleophilic substitution reactions means this nucleophile is going to replace some of the things from other species. Let's see. In this example here, we have this methyl bromide or bromomethane reacts with this KOH in some solvent and forms methanol, an alcohol, plus KBr. This reaction follows this SN2 mechanism, and we'll see exactly how this product is formed from these two reactants. Here you must observe one thing, that this KOH is our source of the nucleophile. So this KOH actually dissolves, you can say, or dissociates, you can call it as K positive and OH negative, and this is the nucleophile which is going to be available now. And this thing CH3Br is called as our substrate. This is the substrate, and our nucleophile is generally called as the attacking reagent. So this is the reagent and this is the substrate. This one is the substrate, and we'll see what happens in this reaction, which is simply a one-step reaction. So SN2 is a one-step reaction. You'll have to remember this. The structure of methyl bromide is something like this, and here the C2Br bond is a polar bond because Br is highly electronegative element. It's a halogen, and we know most of the halogens are very electronegative. Therefore, the shared pair shifts a bit towards this Br, and as a consequence, this is going to acquire a slightly negative charge, and this is going to acquire slight positive charge. And now this Br is actually needs both the electron. It wants to take both the electrons, but carbon will become unstable after that because the carbon must be connected to four things, and then it will lose the electron and become unstable. So it is not breaking, but it is on the verge of breaking. You can say it can easily break if something triggers it. That something is this OH negative now, which is a electron rich species. We can say there are many pair of electrons on it, and really needs a positive charge. So it is interested in this carbon here. So this OH, and there are many of them actually, this is solution, and we are having this OH negative from obtained from the KOH solution. All these are present here. Now, if this OH wants to approach this carbon, it cannot approach from this side because of the presence of this bromine group here, which is an electronegative group, and it can have its negative electric field here, which is going to repel these nucleophiles away. So there is no way that this nucleophile can approach from this side they cannot approach. So these OH, there is no problem. These OH can easily approach this carbon here. So I'll say this OH goes here from the rear side. So they always say that in SN2 only rear side attack is possible, and this is the reason that this Br being a electronegative element is going to repel these species away, and only those species which are this side can approach or substrate or this positively charged carbon atom over here. What happens after that? As this OH is approaching this carbon, these three hydrogen which are here, they get repelled, and maybe they are going somewhere here. We'll see in the structure something like this. This is what you're going to, this is a plane, and all of these hydrogens are repelled slightly away from it. Now here we have this OH approaching, and I will show this OH is approaching, and still the Br is still there. So this bromine has not yet left, and this is what they call as the transition step, or we can say it is an unstable intermediate. This is unstable. That's why we have put this in the square bracket. As you must have seen, they put those nascent oxygen and hydrogen in the square bracket because they are unstable, just to represent that this species is unstable. And why it is unstable, you can easily see, because this carbon is now connected to five things. 1, 2, 3, this is 4 and 5. That's why this is unstable. This is not possible. So what happens here? This OH bond is, you can say that is not completely formed, and this is not completely broken. So it's on the verge of forming and it's on the verge of breaking. And eventually this is going to break completely, leaving this Br negative outside, and this OH will approach this and completely form CH3OH. I'll show you. This is what our product will be looking, say CH3OH. This is our methanol which was expected to form, and maybe that Br which has left with a negative charge, so it's also there, which will afterwards react with that K positive forming KBr. Here, one more thing you must consider, that since this OH can approach from the left side or the rear side, therefore we have a thing called as inversion of configuration. Inversion means inverting the configuration. If you remember, our earlier product, the reactant was something like this. The hydrogen were from this side and we had this Br over here. So all these hydrogens which were this side now went the other side here. So this is the inversion of configuration is happening over here. From this side the hydrogen went the other side. So inversion, that is the inverting of the structure, takes place in SN2 reactions. One more factor which is always discussed is steric hindrance, means the structural hindrance. We have considered methyl bromide in our example. What if we consider a bulky group like a tertiary tertiary alkyl halide, like this one here, CH3 thrice CBr? Its structure will look like this. And as we have discussed earlier, our nucleophile cannot approach from this side because of this negative influence of this Br here, but this OH can approach from the rear side. There is a problem here. There is a very bulky structure which is going to obstruct, that's the hindrance, obstruction to our nucleophile. That's why it's going to find it really difficult to reach this carbon here. And remember, it's not interested in any other carbons which are connected, say this one, because this bond, this carbon is connected to Br. This is slightly negative, and you can say this is slightly positive. It needs that positiveness, this carbon's positiveness. Therefore, this OH, all these OH wants to reach only this carbon here, and they're not interested in the outer one. And it's very difficult because of this bulky structure. They will find this obstruction over here, and that is called a steric hindrance. That is why when they ask the rate of a reaction, we can write like we can say the rate of a SN2 reaction is maximum for a primary. then for a secondary, and least for the tertiary. It's maximum for primary, and it's obvious because as we had taken that example of methyl bromide, you can say it's very easy. For a bulkier group, it was difficult, but here that attacking reagent can easily approach this carbon. It's very easy here. And it's like running in woods here for this nucleophile. It's very difficult to approach this thing. That's why for primary, the rate is going to be maximum, then for secondary, and least for tertiary. One thing is to be remembered here that this reaction is a one-step reaction, and there is no time lag when this OH approaches this carbon and this Br leaves. It all happens at once. This OH approaches and the Br leaves at the same moment. So it's a one-step reaction, and this unstable cannot be isolated. Therefore, it cannot be called as a intermediate product, because intermediate products are the products which may be extracted separately, isolated separately. But since this is where the carbon is having those 5 bonds, it's very unstable and cannot be isolated. So remember, there is no intermediate formation in SN2 reactions. This type of diagram is called as a transition state, or we can say energy profile diagram, in which we show the progress of the reaction. And here you can see these are the reactants and these are the products formed. And this is we can say the reaction coordinate, or this is the way the reaction progresses further. And these are the energy changes happening. Now this curve is showing the energy changes. Remember, if the energy of a molecule is higher, then it is unstable. If it is lower, then it is stable. Here, these are the reactants at this energy level, and see, this is a kind of intermediate, as we have said, or the unstable which is formed in between. Since it is unstable, the energy is really high. So these reactants are first taken to a higher energy level, then they lose energy and form our products. And you can also show some things if you're familiar with the thermodynamical concepts, that this is the difference between the energy of the products and the reactants, which is called as the del H, change in the enthalpy. And this is the energy here, you can see, to which the reactants must be taken before they are converted into products, which is known as what do we call it, the activation energy. So you can remember represent it as del E or del EA. That's the activation energy. And if you're familiar with this thermodynamical concept, you will find this, that the activation energy and the del H can be represented in this energy profile diagram. And since it's a one-step reaction, it will have only this one excitation, or the higher energy level state. Okay, that's it. In the next video, we'll see the effect of solvent as well as the SN1 reaction. We'll compare SN2 and SN1 also, and we will see some other mechanisms. Goodbye.